So that gives us 1/4. And then the probability that the product is larger than 12. Xin, what's your answer? Sorry? 5/12. Product is larger than 12. Is it 5/12, you sure? 8/24, right? Will you do a check? Product is larger than 12. So there should be, it should be the numbers 15, 18, 20, 24, 25, 30, and 30, 36. Okay? Then after that, part 3, probability that the product is a prime number. Bernice, what's your answer? Part 3? 5/24, good. Then last one, product is less than 37. Jiahui. This one? 0. Product is less than 37 then.
24.
24?
1. I mean 1.
1? Okay. So answer is 1. Okay. So now let's look at question 2. Okay, a circular card is divided into 3 equal sectors with scores of 1, 2, and 3. So the diagram shown to you is something like that. Then the card has a pointer pivoted at its center. The pointer is spun twice. Each time the pointer is spun, it is equally likely to stop at any of the sectors. Okay, so they are equally divided. Then after that, with the help of a possibility diagram, we want to find the probability of 2 different events. Okay, so to draw this possibility diagram, okay, what would we have on the x-axis and the y-axis, or rather the horizontal and the vertical? Tishi, what would we have on the? What would you choose to have on the horizontal axis? Spun twice. What would you write? First spin, and then what markings will you give? Okay, 1, 2, 3. And then after that, on the vertical axis, you would have second spin, and then 1, 2, 3 as well. So you have this possibility diagram. Okay, what's the probability of having each score to be a 1? Hui Ming, what will your answer be? The probability that each score is a 1. 1. Probability is 1. Can it be? What does probability equals to 1 mean? It should be 1/9, right? Okay. What about part 2? The probability that at least one score is a 3. What would that be? Benjamin? What would the probability of at least having one score is 3? 5 out of 9. Okay, so you could have this case, and this case, right? So the answer will be 5 out of 9. It says that in a game, a player spins the pointer twice. His final score is the larger of the 2 individual scores if they are different, and their common value if they are the same. Okay, so there's different condition given in this case. Alright, so the possibility diagram below shows the player's final score. Okay, so in this case, this possibility diagram, there is no operation involved. So you need not actually put in anything in the top left hand corner. Okay, so you just need to put in the numbers here according to how the situation has been described. Okay, so the final score is the larger one, right? If they are actually different. Okay, so in this case, this will give you 2 and this will give you 3. And if they are the same, 1, 1, the score will actually be 1. Okay, then after that, this will be 2, this is 2, and then this is 3. 3, 3, 3. Okay, so this will be how the possibility diagram will look like. Okay, part 2, we want to find the probability that the final score is even. Okay, so what would the probability be, Eugene? 1/3. Okay, how do you get 1/3? 3 out of 9. Good, so 1/3. And then the probability that the final score is prime, Charan? 8 out of 9. So everything except for 1. Okay, because 1 is not a prime number. Okay, so next we will move into looking at tree diagrams. Alright, we will first understand how a simple tree diagram look like first. Okay, later on we will look into how we can compact everything in. Okay, so a simple tree diagram. Okay, why do we need to use a tree diagram? Why doesn't a possibility diagram isn't it sufficient already? Okay, this is not sufficient because there's only your horizontal and vertical axis. Okay, you can only consider 2 situations. What if I need to do a third spin? Okay, I'm definitely not possible. It's not possible for me to start drawing x, y, and z axis. Okay, I cannot possibly draw a 3D diagram. Then you have dots everywhere. Okay, I don't think you are capable enough to have dots so clearly and visibly for you to do counting, right? Okay, so that's why we need to introduce a tree diagram that will allow us to have situations where there are 2 or more different components. Okay, more than 2 components. Okay, so for example, if we were to consider the tossing of a fair coin, or rather 3 fair coins. Okay, so the coin will either have a head or a tail, right? So you toss the first one first. You will consider head or tail. Okay, so in this case the key would be H will represent head and T will represent tail. Okay. Then after that you toss the second coin. And then you have head or tails as well. Okay, it is either the case whereby first coin is head, second coin is head, or second coin is tail. Okay, so there are many combinations involved. So a tree diagram will be able to illustrate for us the different combinations along the branch. So all these lines over here, please use a ruler to draw. They are what we call branches. That's why it's a tree diagram. Okay, then after that third coin, once again, there's a possibility of either head or tail. Okay. So in this tree diagram itself, we are able to see that the total number of possible outcomes, okay, of tossing 3 fair coins, meaning to say the different possible combinations that could be. You can have one combination, all heads, okay, two combination, two tails, one head, okay, depending on the coin as well. Okay, then after that 3, 4, 5, 6, 7, 8. You can have a total of 8 different outcomes. Yes.
Must we draw this?
Sorry?
Must we draw this?
In what?
Pencil.
Pencil. Yes, you can draw this in pencil. Okay. If you draw in pen, I mean you can. The reason why you draw in pencil is because so that you can erase, right? And as I explained yesterday, you will only be given writing space. Okay, you will no longer be given this gap. Okay, so using this tree diagram over here, let's look at work example 5. So it also talks about 3 fair coins being tossed. Why is it that the question always say must be fair coin, fair die? So that it is equal probability. The probability of getting head and tail is actually half each. Okay, so that the calculations will be consistent. If it's not fair, then the probability will be changed already. Okay. So we want to first find the probability that there are 2 heads and 1 tail. Okay, so 2 heads and 1 tail, that will actually be having this option. Okay, 2 heads and 1 tail. Then after that, or else this option as well, 2 heads and 1 tail. Okay, so there are 2 combinations that will give you 2 heads and 1 tail. Right? Okay, sorry, one more over here. Did I miss out any more? No. Okay, so there are 3 different combinations. So there are 3 different combinations that will satisfy this event. So therefore, the probability is 3 out of 8 different outcomes. That there's at least 1 tail. So in this case, at least 1, so it's either 1, 2 or 3. Okay, so that means that it is actually practically everything except having the all heads. So you could consider it as 1 minus 1 over 8 equals 7 over 8, or you could count in this case to be easily 7 over 8. Okay, so it depends on how you see it. In this case, it will just be a 1 mark question. So answer right or wrong, the mark will be given accordingly. Okay, I want you to try practice now 5. Question 1. Draw a tree diagram according to the situation where it's about hitting the bull's eyes. Okay. Hit or miss. Okay. So you can have a key that says H represent hit and M represent miss. Okay. Yes. Yeah.
We need to write the first one, second one, third.
Yes, you must write down first coin, second coin, third coin. This is everything of a tree diagram. Okay, everything that is in black. Yes, the key is part of it. Or else how would I know that H stands for heat and M stands for mass? For question 5.